Hello there, my name is Charles Sipa. Welcome to another presentation on limits. In this case, we're going to deal with a formally and more precise definition of a limit, normally called epsilon delta definition of a limit. So we call that, we are now familiar with this kind of an expression. We say limit of f of x as x is tending to a is equals to L. Remember that this is our first kind of a definition of a limit, which is very intuitive and very practical, introducing this notion of a limit, but is not very precise, because here we're saying x is getting closer and closer to a, closer and closer to a, but how close is not very precise. So because of that reason, we need to develop we need to define this notion of a limit in a more precise way and see if we can try to have a measure of how near x should be in order to have the values of f of x approaching the value L. So let's start this way. Let's say we've got a line 2x plus 2, which clearly we can see that when we calculate the limit as x is approaching 1, that is limit of 2x plus 2 is equals to 4. So our question is now is how close should be the values of x to 1 in order that the values of the function 2x plus 2 approach 4 or get close to 4 as we wish. So for that, let's look at the following sketch. Let's suppose we want the values of the function to be within a distance of half from 4. So we want to check what condition can we impose on the values of x, or at least what distance within which we should take the values of x. Distance from, in this case, 1, should we take the values of x in order to guarantee that the values of this function are within the distance half from 4. So talking about distance, in that case, we have to evoke the absolute value function, because remember the absolute value function, like when we say absolute value of x, we actually mean the distance of this number x from the origin. So now if we talk about the distance of the values of this function from 4, we then write 2x plus 2 and absolute value, let's put brackets here, minus 4 is less than 1/2 according to our requirement here. So given that we want to have the values of function within a distance of half from 4, we then need to determine how close we should get the values of x, how close to 1 should be those values of x. So what we can do here is the following. We simplify this as follows. Simplifying within the bracket, removing the brackets within the absolute value, we get 2x minus 2 is less than half. And then going further, simplifying this, we see that this is same as 2 in brackets x minus 1 less than half. So we can see now the transformation we've made here is actually giving us an expression which is getting us closer to talking about the distance of x from 1 in terms of absolute value. So this we know that it means that 2x, so 2 in brackets x minus 1 is less than half and greater than minus half. So dividing both sides of inequality so that we can in the middle, we can only have x minus half. We get to x minus 1 less than 1/4 greater than minus 1/4. So which is also equivalent to saying absolute value of x minus 1 is less than 1/4. Sorry, I said 1/4, but I wrote 2. That should be 1/4. So what does this mean now? So it means that if we want to guarantee that the value of the function is within a distance half from 4, then we must take the values of x within a distance less than 1/4 from 1. So now what we want to do now, we want to go further discussing this in a general way, whereby we're not like choosing a number like half or a quarter, but choosing any actual number, in this case, which we're going to denote by epsilon. In this case, epsilon should be an actual number greater than 0, which you can choose as small as we want or wish. So that takes us to this following discussion. Let's say, for example, we show that we can make the values of the function 2x plus 2 be within a given distance epsilon greater than 0 to 4, no matter how small epsilon is, by making x sufficiently close to 1. So that takes us to the following. So in this case now, what we're starting off with, we're starting off 2x plus 2 within a distance from 4 less than epsilon. And the epsilon here is an actually small number. So then, doing the same kind of manipulation we did before, we have here 2x minus 2 less than epsilon, and then simplifying, we put here 2x minus 1 less than epsilon. Again, this means that 2x by x minus 1 is less than epsilon and greater than minus epsilon. So again, dividing both sides by 2 to have in the middle here x minus 1, which will actually take us to the distance from x to 1. We have minus epsilon divided by 2 less than x minus 1 less than epsilon divided by 2. So this equivalent takes us to distance x from 1 is less than epsilon over 2. So now, what again this suggests to us that if we choose x within a distance of epsilon divided by 2, never mind how small this epsilon is, we're going to have the values of the function within a distance less than epsilon from 4. So this kind of discussion takes us to a more precise definition of a limit. So before we get to the definition of the limit, we're first of all going to look at a this situation whereby we're looking at a limit of a rational function where this rational function is actually not defined. So what we need to do here, we can again choose ultra small number epsilon. Then we require that the values of the rational function be within a distance less than epsilon from 15. So we write 3x squared minus 3x minus 18 all over x minus 3 minus 15 is less than epsilon. Now, simplifying this expression, maybe let's shift these things a bit. Then we can start playing around with this expression, manipulating it to see within what distance can we take the values of x so that we are guaranteed of the values of the function being less than epsilon from 15. So we see that this is equivalent to, first of all, here what we're going to do, we're going to write this as a single fraction. Now, going further here, we're going to continue in this place here and write, simplifying here, we can see that minus 3 and minus 15 will make us will give us minus 18. So we've got 3x squared minus 18x, and then we've got minus 18 plus 45, missing a bracket here, plus 45, which will be 45 minus 18, which is going to give us 27. So we've got here plus 27 divided by x minus 3 less than epsilon. Now, we now see that we can take out the common factor in numerator, which is 3. Then we've got the following. We're going to have 3 here, and the x squared minus 6x plus 9 x over x minus 3. And then we see that what in brackets here we've got a perfect square, which will simplify as follows. You can see now we can simplify this factor with one of numerator. Then we've got here, which is equivalent to saying 3x minus 3 is less than epsilon greater than minus epsilon, which equivalent gives us, dividing both sides by 3 here, we've got here that we've got x minus 3 less than epsilon divided by 3. So now we see that what we have here, if we want to guarantee that the values of this rational function are within a distance epsilon from 15, we must actually choose the values of x within a distance of epsilon divided by 3. So now, with these two examples, one with the linear function, and now with this rational function, now we can come up with a more precise definition of the concept of limit, and with an idea of how close, every time we choose epsilon, we can sort of have an idea how close we must choose the values of x, so that the value of the function can be within a chosen distance epsilon from the limit. So now this kind of formal this kind of discussion originated from a lot of debates about the impreciseness of the initial definition we had before. Hence we've got such kind of writings which says for a good definition of limit and what we mean by close, we need the epsilon delta definition created by Carl Weierstrass. Actually, this definition is a very important definition to understand, and we recommend that you study your text and look at the examples so that you understand this definition thoroughly, because it actually forms the basis of mathematical analysis, which actually calculus prepares you for. And then you start with this definition, you start having some kind of idea of how mathematical analysis is done, or how we generally work in mathematical analysis. So the definition is as follows. It says, when you say limit of f of x tends to 0, that is equivalent to if and only if, it's just simply saying, is equivalent to saying for every epsilon greater than 0, there exists a delta greater than 0, such that whenever x is within a distance less than delta from a, then we have the values of the function within the distance epsilon from the limit L. So what we saw with the linear function, first of all, we saw that if we want to have the values of the linear function 2x plus 2 to be within a distance of 1/2 from 4, we saw, which you could consider this to be our epsilon, then we could choose the values of x within a distance delta equals to 1/4. And then when we considered epsilon, the arbitral epsilon, we also saw that if we want the values of function to be at a distance less than epsilon, then we had to choose our delta to be equals to epsilon divided by 2. And also we saw the same with the rational function. So this kind of definition actually is more precise, and it gives you an idea of how close you must choose your x, how close to a you must choose your x in order to guarantee that the values of the function are within the distance epsilon from L. Now, what you saw in the two exercises, the kind of manipulations we did to do this, or these similar manipulations we did when we were calculating limits of rational functions, factorizing and simplifying factors, and then evaluating limit. Others, for now, I will urge you to take your text and look at the similar examples and try to solve the similar problems and get used to these kind of manipulations. Others, for now, thank you for listening. Meet you in the future discussions.